Hey guys, welcome back. We're going to start on section 12A when we're talking about different representations of trig functions, and we're talking about Pythagorean identities. This idea of identity just means statements that are true. Okay, so keep that in mind when we're talking about this. We're going to focus on the part of the unit circle that we are very, very familiar with. Okay, so you've known this like the back of your hand, that when we're talking about going around the circle, we've got theta is 0, here's pi over 6, pi over 4, pi over 3, and essentially these are special right triangles. We also know that in the unit circle, this radius here, and therefore here, here, and here are all 1. So if I go back to something that we know really well, so for example, if I were to draw this right triangle here, I know already that this hypotenuse is 1, and that its x value and its y value are here. Well, I already know that the Pythagorean theorem for every right triangle is any of its two legs squared and finding the sum equals the hypotenuse squared. Well, in this case, we know that 1 squared is just 1. We also know that if this is theta, that x equals sine theta, and that y equals, oopsie, I did that the wrong way. That x equals cosine theta, pardon me, and that y equals sine theta. So we can also say that this is cosine squared x plus sine squared x equals 1. This right here is the big deal. This is the Pythagorean identity that bears 8 other Pythagorean identities. So the other things that are true is, what if I wanted to rearrange this to get something by itself? So let's say I subtracted cosine squared to the other side. So if I subtracted cosine squared to the other side, I would get sine squared x equals 1 minus cosine squared x. So this is also an identity. And then lastly, if I took it from the original, if I subtracted sine squared, we would get cosine squared x equals 1 minus sine squared x. So we have 3 different Pythagorean identities, all true, from the same unit circle. But these are helpful when we're either given different values around the circle or we're looking for different values. Now that we know those 3 main Pythagorean identities, keep in mind, if you're going to memorize one, this is the one you want to keep memorized because everything else can come from it. Let's start talking about some reciprocal Pythagorean identities. Remember that reciprocal means that I divide by the reciprocal. So to find these reciprocal identities, first, we're going to divide both by sine squared and cosine squared. So I'm going to divide everything here by sine squared, all over it.
He didn't tell the disciples to go right away.
So we're going to go sine squared divided by sine squared is just 1. And I know cosine divided by sine is the equivalent, we just learned this, of cotangent squared. And 1 over sine is cosecant squared x. So this is our first reciprocal Pythagorean identity. We can rearrange this to also find some other things. So if I subtract cotangent squared, I'm going to get 1 equals cosecant squared minus cotangent squared. I can also subtract the 1 and we'll get cosecant squared x minus the 1 equals cotangent squared x. So we have 3 that have to deal with cotangent squared and cosecant squared. Let's look on the other side. So again, based on our original OG, instead of dividing by sine squared, let's divide by cosine squared on everything. So when we look at this now, we're going to simplify. I know sine over cosine is tangent squared x. Cosine squared divided by itself is 1. And 1 over cosine squared is secant squared. So now we have an identity that has to deal with tangent and secant squared. I'm going to rearrange some stuff to find some other 2 identities. So we can subtract tangent squared from both sides. We're going to get 1 equals secant squared x minus tangent squared x. We can also subtract the 1 and we'll get secant squared x equals, go back. If I subtract, I just said subtract the 1, we would get tangent squared x equals secant squared x minus 1. So here we are. We've got our 9 different Pythagorean identities that we can use depending on what is the most valuable. Keep in mind, again, we're looking right here to see that's where everything comes from. So we're going to use these trig identities to write each expression in terms of a single trig identity, aka we're just going to simplify what we know. So the first thing is that I know that tangent can be rewritten as sine over cosine. And I know if I multiply this cosine here, I can't rewrite cosine as anything else. I notice that this cosine divides by cosine, which cancels to a 1. And this is just sine x times 1, which is sine x. So this simplifies fully down to a single trig identity. The second one here, I'm going to look for where do we find an identity that's equivalent to 1 minus cosine squared. Well, I know up here at the very top, I see here, we've got 1 minus cosine squared equals sine squared x. So I'm going to replace this 1 minus cosine squared with sine squared x as its equivalent, divided by cosine squared x. Well, I know sine over cosine is just tangent, and we've got a single trig function. So here we go, third one. Let's look for something that's equivalent to cosine squared plus sine squared. We see it right here at the top. We know cosine squared plus sine squared is 1. So we're going to replace it with 1 over. And then I know sine, we can't rewrite it as anything else, it's just sine. But secant can be written as 1 over cosine. So if I simplify this, we still have 1 in the numerator. Sine squared over 1 over cosine is sine over cosine. I also know that sine over cosine is equivalent to tangent. And finally, our reciprocal of tangent, 1 over tangent, is cotangent x. So this is our simplified single trig identity. So here's our tips for doing this. Make sure that you rewrite everything as much as you can in sine and cosine, right? Every reciprocal trig identity can be reduced to either sine or cosine. If it's a squared trig function, look for its Pythagorean identity and then use your math to simplify it down into one trig function. Okay, so we're going to use these trig identities to solve the trig equations for one circle, and we're going to find those exact values. So here's the deal. I've got secant squared here, but tangent, and they don't talk to each other. So we've got to figure out a way to write this either all as secant or all as tangent. Because this has a squared, I know that I've got an identity that can deal with Pythagorean identity. So let's see what's equivalent to secant squared x. Looking up here, I can see right here, we've got secant squared x, which is equivalent to tangent squared x plus 1. So we're going to put that right here. So this secant squared x is going to be tangent squared x plus 1. Now I'm going to bring everything back down. This looks like a quadratic. So just like we learned last section, when I've got a quadratic, we're going to set everything equal to 0. So let's minus the 1 here. And when we simplify, we get 0 equals tangent squared x. 1 minus 1 is also 0. And we have plus the tangent x left. Now we're going to factor. We always look for a GCF first. We've got tangent on both. So this is going to factor out a tangent x, and we're left with tan x plus 1. Now we can use the zero product property. So I know tangent x is going to be 0, and tan x plus 1 will equal 0. And this simplifies it for us so we can solve both sides of the equation. So I know that x is going to equal inverse tan of 0. Where does tangent equal 0? Well, I know that means, okay, that means sine and cosine's got to be a 0 somewhere, right? So remember that inverse tan equals 0, because if tangent equals 0, then sine has to be 0. So where does sine equal 0? That's when the y value is 0. So that's here and here. And that's between 0, pi, and 2 pi within that one circle. Let's solve the right side. Subtract the 1 on both sides. So we get tangent x equals -1, which means inverse tan of -1. Hey, that means that both sine and cosine have to be the same value, right? Tangent equals a 1 at a pi over 4, but remember tangent is going to be negative in the second and fourth quadrants. So a pi over 4 angle here and here is going to be 3 pi over 4 and 7 pi over 4. And those are all of our values for theta within one positive circle. Last one before we go, so here I see a sine squared and a cosine squared. Again, they're both Pythagorean. We need to figure out a way to get them to the same trig function. So either you can replace sine squared or you can replace cosine squared. I'm going to replace cosine squared. So where do we see something that's equivalent to cosine squared? I see cosine squared equals 1 minus sine squared. So let's go back over here. So I'm going to replace this cosine squared equals 1 minus sine squared. So I'm going to bring everything else down. So this 2 goes here, and this is going to come straight down. Now we're going to combine like terms. 1 plus 1 is 2. Negative sine squared and another negative sine squared is 2 sine squared x equals 2. This is not a quadratic. So, well, it is squared, but we don't have to solve this like a quadratic. We can solve this directly. So we're going to subtract 2 from both sides, and I get negative 2 sine squared x equals 0. Divide both sides by negative 2. We get sine squared x equals 0. To get sine by itself, we can take the square root of both sides. It's plus or minus. But remember, plus or minus 0 is still just 0. So I know, hey, we've got sine x, got to equal 0. To get x by itself, take the inverse. Where does sine equal 0? We know it happens here and here, which is x is at 0 pi, pi, and 2 pi within one positive circle. That's it for today. See you in class.